We return with Chapter 11 about sampling distributions, especially sampling distributions of the sample mean. We're now going to look at the situation where our population is not normally distributed. Now we know that if our population has a normal distribution, then the sampling distribution of the sample mean is normal. But what happens if the population doesn't have a normal distribution? Well, we saw in that example of the picture of the histograms, and when we looked at samples of size 10 from that very skewed distribution, that as our sample size got larger, our sampling distribution became approximately normally distributed. So what we're going to find is that we have what's called the central limit theorem, and it says regardless of the shape of the population distribution, the sampling distribution of the sample mean becomes approximately normal as the sample size increases. But what exactly does that mean? Well, for all other random variables x, for all other populations that are normally distributed, the sampling distribution of the sample mean is approximately normally distributed if n is 30 or higher. That's the convention for our class, for n being large enough. So if we have a sample size of 30 or more in a sampling distribution, we can assume the sampling distribution, the x bar, is approximately normally distributed. So let's see how that works. We're going to look at this problem. The most famous geyser in the world, Old Faithful in Yellowstone National Park, has a mean time between eruptions of 85 minutes and a standard deviation of 21.25 minutes. The distribution of the time interval between eruptions is not normal. So let's look at part A. What is the probability that a randomly selected time interval will be less than 75 minutes? Now we're talking like a Chapter 3 problem, except since our distribution is not normal, we don't know how to calculate this probability with the tools we've been given in the class. So we can't even do part A. Now let's read part B. What is the probability that a random sample of 20 time intervals will have a mean less than 75? Well, here I see a sample size, and I see that they're asking for the probability of a mean less than 75. That's showing me that I'm in a sampling distribution. But it's coming from a population that isn't normal, and our convention is if our sample size is at 30 or larger, we can assume x bar's distribution to be normal. So we can't do part B. Well, let's see about part C. It says, what is the probability that a random sample of 30, I've got a sample size of 30, and it rings a bell that 30 or greater, I can now do probabilities because my sampling distribution becomes approximately normal if my sample size is 30 or greater. So I want to find that probability that the mean is less than 75. So I'm going to have to find the sampling distribution and then calculate this probability. So what I would do is I'd say the probability that x bar is less than 75, and now what is my sampling distribution? Well, it's got a mean of 85, and my standard error is 21.25 divided by the square root of 30. So when I'm finding that mean less than 75, I would now say the probability that z is less than 75 minus 85, that difference divided by 21.25 divided by the square root of 30. That gives me the probability that z is less than negative 2.5, and that probability from our table A is 0.0049. So that's how we do part C. It is a sampling distribution problem. Part D, what is the probability that a random sample of 30 time intervals will have a mean greater than 100? Once again, we're in a sampling distribution, and since our sample size is 30 or more, we can assume that this x bar is approximately normally distributed, and it's going to have the same distribution as C. So to find the mean greater than 100, I would say probability that z is greater than 100 minus 85 divided by 21.25 divided by the square root of 30. So that will give us the probability that z is greater than 3.87. And you'd look on your chart and you'd say, whoa, there's no number 3.87, but remember what our convention was. If the number is off the chart, then you're going to go and say, you're going to look at that probability, and you're going to say the probability is less than the very last number you see on the chart, which is 0.0002. So the probability of that happening is less than 0.0002. Very, very small. And the last problem, the probability that a random sample of 30 time intervals will have a mean between 75 and 90. Well, we're in the same sampling distribution as we were in C and D, so we just standardized 75 and 90. We get the probability of C being in between negative 2.58 and 1.29. That gives us 0.8966. So that's how we'd work this problem. Now let's see how we can use Minitab to help us do this. So we don't need the table. So we're going to see how we would answer part C, D, and E using Minitab. Well, first of all, we'd have to calculate our standard error. And this is how we do it. Remember, in Minitab, we have a constant, and the way we do constants is K and a number. So we use the command let K1 equal 21.25 divided by the square root of 30. We're now finding that standard error. And if I wanted to see what the standard error is, I'd say print K1. And you see what Minitab would display. It would say data display, and it would say K1 3.87970. So that's the value of our standard error. So remember, part C asked us what the probability that the mean was less than 75. We can use Minitab to help us. We use the command CDF for cumulative distribution function. So in other words, it's just like table A. So we say we want the cumulative distribution function where we're looking at 75. So we're looking at the probability of 75 or less. And we're saying, hey, put that probability in K2. Semicolon, because this is going to be a subcommand because Minitab does not know what distribution you're looking at. So we let it know in the subcommand that we're looking at the normal distribution, but we need to give the mean and the standard deviation. And for this problem, remember the mean minutes between eruptions was 85, and the standard deviation was the standard error we just calculated, so we can just put K1. And when we print K2, that's going to be the probability that X bar is less than 75. And note that we did get the same answer we did when we looked, almost the same answer we did when we looked it up in the chart. Minitab will be a little more precise. So let's look at part D and how you'd use Minitab to do greater than. So we wanted to find X bar greater than 100. Well, again, now remember, the CDF gives us everything less than. So if we say the CDF of 100, we're saying what's the probability of being less than 100. So we're going to use the complement rule at the very end, and you'll see what I mean by that. So we say CDF of 100, put that probability in K2. This is a normal distribution, so in our subcommand we'd say normal with a mean of 85 and the standard error K1. Now we're going to say let a new constant, we're going to call it K3 equal 1 minus that probability. Because remember, that probability was everything less than 100. We wanted everything greater than 100. So we'd have to do the complement rule and say 1 minus K2. And then print K3, and we'd have that probability. And remember, we figured it to be much less than 0.002, and it was. Then we did part E, where we wanted to find the in-between. And this, again, is how you can use Minitab. You'd say you'd want the CDF of 75 and less, put that in K2. Let it know that it's a normal distribution with a mean of 85 and the standard error we calculated K1. Then we'd have to do 90 or less. So the CDF of 90, put that answer in K3. Again, let it know that it's a normal distribution, give the mean and standard error. Then you see let K4 equal K3 minus K2. So we got the 90, the probability that one was 90 or less, minus the probability of 75 or less. That would give us that in-between. So then we'd say print K4, and we'd get 0.896283, almost to what we got when we calculated it. So this is how we would use Minitab, and you can take a look at these commands to help you when you're trying to find these distributions. And here's our